This video explores the micro-to-macro disconnect in dielectrics and polarization, showing how a single dipole at the quantum scale scales up to a macroscopic bulk material. A common misconception is that a molecule's ground state dipole moment directly dictates bulk material properties. In reality, bulk dielectric constant and thin film polarization are complex, depending on orientation, phase constraints, and environmental response. Scale 1 is the isolated ground state. The molecular ground state dipole moment, mu, is a fundamental property calculated or measured in isolation, entirely free from external influence. Scale 2 is the volumetric ensemble. Thin film polarization, P, is the collective response of many molecules, defined as the dipole moment per unit volume. The film property is a combination of molecular dipole, orientation, density, and interactions. The vector cancellation model shows that even if every molecule has a strong dipole, a thin film will exhibit zero net polarization if the molecules are randomly oriented. Randomization mathematically erases the bulk dipole. In the mythical perfect alignment, molecular and bulk dipoles are equivalent only in a perfectly idealized system. In a thin film, only the projected component perpendicular to the surface contributes to the macroscopic dipole. In real-world environments, the isolated molecular ground state is heavily altered. The molecule's inherent dipole is just one ingredient in a complex physical landscape, influenced by surface, bulk, and interface levels. The bulk dielectric constant measures how strongly a material polarizes in response to an applied electric field. It is a measure of dynamic susceptibility, depending purely on how dipoles react, not just what they possess. When subjected to a local electric field, the total dipole of a molecule transforms. The dielectric constant aggregates three distinct physical responses: electronic polarizability, ionic/vibrational polarization, and dipole reorientation. In polar liquids, the dielectric constant relies on the statistical ability of permanent dipoles to align with the field, fighting thermal chaos. This is influenced by dipole strength, density, and temperature. The lock-and-key constraint of solids means that rotational freedom vanishes, and permanent dipoles are often physically locked. The solid-state dielectric constant must rely on electronic polarizability, lattice vibrations, or domain motion. Different states of matter show varying dielectric signatures. For example, polar liquids involve dipole rotation, leading to a large bulk dielectric response, while molecular solids have minimal dipole contribution. The grand principle of macroscopic polarization is dictated by freedom. A large dielectric constant requires not only large individual dipoles, but also dipoles that are structurally and thermally free to respond to an applied electric field.